This video is part of CAE Associates Ansys e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an Ansys channel partner since 1985 and have developed our Ansys e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of Ansys courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
Our topic today is working with shell beam solid meshes in Ansys Workbench 14.5. I'm George Bauer. One thing I also wanted to mention in regards to today's topics, we'll be looking at how to join various types of meshes and utilize and post-process that method. But we also have another webinar on our website, Meshing 2 with Shells and Beams. It's a related topic in connecting those types of meshes that might be helpful for you. Okay. Why don't we get started here? I've got a demonstration problem. Before we go there, just in terms of working with shell, beam, solid meshes in finite element analysis and simulation, we have a large toolbox of element types to utilize to best represent our physical structure. Many times, given our parts and our scenarios, a combination of those element types are necessary to capture the behavior most accurately. So in this webinar, we're going to look at scenarios and how to connect those varying element types in a single analysis, single structural analysis. We'll look at the line, surface, solid body geometry, the mesh, and how to connect those in mechanical. And using these combinations can create both an accurate and an efficient model. Okay, so with that, let me move over to Ansys Workbench. I've set up a project schematic here with a number of models. So I've got some specific examples to go through. So with the first model, let me bring that up. We're going to take a look at our geometry first. In this model, I have a tube-like structure. Say we have some tube that's intended to use like a moment arm and a wrenching action here. In the Design Modeler, whether you create it from scratch in Design Modeler or you're importing, you'll see Design Modeler tree have the surface bodies. These surface bodies will be meshed with shell elements when we bring those into mechanical. The solid body here I've included. This will be meshed with solid elements, but note perhaps this may be an insert to this tube. Maybe this is a different material or a different thickness. So we'll want to connect this thin tube to our insert towards the bottom. We'll kind of use this as a cantilever beam end. Also note that I have a tube here. This is kind of an extension. It's not directly linked into this multi-body part. So this multi-body part will be meshed consistently so that they share nodes along the boundary. I just want to demonstrate an additional method of attachment for this shell tube as well. In Design Modeler, you can specify the thickness for each surface body. Now that'll translate into mechanical as the shell thickness. Okay, so let's move over to mechanical for this model. So I want to go through the overall analysis scenario and show you some of the neat features within mechanical. When the bodies come into mechanical, you'll see our parts here. When they do come in, this is where you want to specify the material assignment. You can see I've already meshed this part here. And you can see with this separate tube, we actually have a mismatch mesh along the boundary here. So we'll have to create a connection there. And then we'll have to create a connection of the tube down to the solid insert. If I take a quick look at our resultant load to give you kind of the analysis scenario, we're going to put a kind of a cantilever shear load of 100 pounds at the end and ground the solid insert here. Okay, so let's take a look. First thing I wanted to show you, when the thicknesses come in for the surface bodies, These we can look at the visualization. If once the part has been meshed with the thicknesses assigned, we have on the View menu an option to view thick shells and beams. So even though these are surface elements, you can kind of see that with the surface element, the thickness of the shell is actually represented. Sometimes this is helpful for reviewing part-to-part fit and what have you, making sure you can confirm the right thickness of the shell elements. Also want to show with each tube, with each surface body, is an important part is the offset. The offset controls, typically the surface bodies are modeled at the mid-plane of the solid that you may be extracting. Surface bodies are great for modeling, creating shells for modeling fairly thin to moderately thick structures. But by default, the middle, the actual element geometry is in the middle of the shell thickness. You can, let me hide this body. You can control the offset type on the body itself in the geometry, and where if you have the offset type as middle, let's turn on. Let's switch over to our mesh. There, so that you can see the thickness here. Now, if we had our tube here and we set this offset to, let's get to this body here. If we set this offset from middle to top, you can this surface body would actually be the top of the shell. You can define that, and then the mesh would be correspondingly extrude inwards. And now you can see the difference there between setting the top, middle, or off or bottom representation of the surface body. So that's helpful in controlling that. You want to make sure you're modeling that properly. So that's the visualization with the shells. Next thing I want to show in some of the visualization with surface bodies and connections, one thing that is helpful is looking at, we notice here because we had distinctly separate bodies that there was a mismatch in the mesh, but sometimes you can't always see that. So one of the things I like to help along with that is view by connection. You can change the display by connection for the surface bodies that shows all the free connections here. So you can display that both on the geometry, both on the mesh. You can see that everything highlighted in red is a single free surface. Where you actually have connections, you can see multiple connections here. So with this, it kind of highlights the fact that we do have an issue in this region here that we have to use a connection for. So let's start off by attaching these parts together. First, let me show all the bodies here. Let's start off first here with a mesh connection attaching these two tubes. And the mesh connection works well with surface bodies because you can connect two distinctly separate bodies but have it mesh so that they're congruent or share the same nodes across that boundary. This is also helpful if you do have small little gaps or mismatches between the surface edges. This will actually help take in that gap and create a congruent mesh. So in the Mesh Connections folder, we can insert a mesh connection, create a master geometry. I'm going to select one side of our tube on this side. Let me select that edge, highlight that as being the light tan body, select all those edges, assign that as to the master, and then select the slave tube. See, that's the darker brown. Select all those edges on the tube extension. You hit apply, and then we have distinctly we're showing the mesh connection there. Another visualization tool to help when we're setting up either contact or mesh connections is the ability to select body views. Body views actually shows whether it's master or slave, contact or target, lets you look at both sides of this, in addition to all the bodies at once. So you can see here with the red side being the master is being displayed here, and you can confirm that the slave is on the other side. So you can individually confirm here, making sure we get the right edges for the right parts. And while we update the mesh here, we'll now should see this enforcement of connecting the meshes. Next thing I'd want to do, here we can see that, And our visualization shows that the red line indicating free edges is now gone because of the connection. So now that we've connected the pipe to the main elbow here, let's go take a look now what we need to do with the surface bodies to our solid body. In fact, let me go back, change our shell thickness here. There we go. Back to the middle representation. And you'll see that we can confirm that the outer profile of the solid is consistent to that. Next connection I'd like to demonstrate here is the use of contact between different types of geometries, surface bodies and the solid bodies. So in our contacts folder, we can insert a standard bonded contact. And with the bonded contact, we're going to set up a specific MPC-based contact. With this MPC-based contact, the contact side has to be the surface body. So let's go ahead and select this end of our tube here, select all the edges of our tube, and apply that to the contact side. You see here we got the contact side. And then for the target, you can see we have various select modes. I'm going to select the surface of this insert, if you will. Perhaps it's welded on or inserted. Let's go ahead and apply that to the target. So this kind of confirms our contact pair. Let me turn off the body views. With this now, what we have to additionally set up is the information in the details of this contact pair. It's set to bonded. However, we want to switch the formulation over to MPC-based contact so that we can couple the rotation degrees of freedom coming in from the shell edges to the solid elements. The solid elements only have translation degrees of freedom, so you're essentially transforming the rotations of the edges of those shells into the attached nodes of the solid structure. So that assures some more of the continuity. And so you can control the type of coupling. Even if you perhaps did only want to uncouple those, you can set that, but we're going to keep that as coupled to those shells. Okay. Those are the two types of connections I want to demonstrate with this example problem. Let me shoot over to a completely solved problem just to show you some of the post-processing things you want to take a look at when you are making the connections and working with shell bodies. You typically want to make sure that your deformed shape is consistent. You know, you have a deformed shape with a consistent displacement profile with everything connected. Also looking at stresses. Some of the things working with stresses in mechanical here, you want to take a look at for surface bodies. You want to understand, are you looking at stresses along the top of the body? Perhaps you're looking at the top of the surface of the shell or the bottom of the surface of the shell. So let me get rid of our solid entity temporarily. And so when we look at stresses by default, we're looking at that when you view the top of the shell, it is the top surface stresses, and the bottom of the shell, that's bottom surface stresses. Let me turn back on our thick shells and beams here. So the visualization in mechanical does show a gradient through the thickness when you turn on the shell visualization. You can control just plotting whether you want the top only for the shell or the bottom only. You can control that with a pull-down menu. So you have that ability. Some of the post-processing specific to the bonded contact we inserted to connect these two. When you have bonded contact pairs and you're interested in the load being transferred across that bonded contact pair, you can insert a force reaction probe. You can, under the probe menu, you can see this force reaction probe. Let me show all of our bodies. The force reaction probe essentially looks at our bonded contact region, and there's our 100-pound value of shear being transferred across this bonded contact pair. Just to show you where that is from the probe menu, if you go to force reaction by default, it's looking for a boundary condition, but you can switch this over to a variety of options. In this case, a contact region. We can specify our bonded contact and then obtain those results. And you can also do this with moments as well. Okay, so that's a couple ways to post-process this type of model and ensure that everything's connected and you understand the load transfer across. with this, that's all I wanted to show with this model. So this brings us to a point where we can start our first poll. Just interested in setting up a poll here while I get our other model ready. Interested in everyone attending that what type of mesh do you typically use to perform your analysis? Do you usually use solid elements or shell elements? Do you, in fact, use beam elements or some combinations of shells and beams? And then also, perhaps you do combine everything, all the solid shells and beams together. So I'll give you a few moments to fill that out while I close out this model. Bring up our next model. Okay, a few more seconds. We'll take a look at those results. Okay, it looks like some of the attendees here are working primarily with solid elements. A few are working with just shells or combinations of shells and beams, and then many are working with combinations of all the above. I appreciate your participation in the polling. So it looks like we have a kind of a wide variety of folks using different element types. Okay, the next model I want to show you is working with beams and shells. And in this example problem, I brought up design modeler. Similar tube, but I've gotten rid of our tube extension. Perhaps we want to idealize that with a line body. So from the view menu, we can control in terms of our tube, our line body, how our line body is displayed. This line body will be meshed with beam elements. We can essentially, when we bring in the line body into Design Modeler, or we create in Design Modeler, much of the access to creating the line bodies is from the concept menu. Whether you're creating it from points or sketches or existing geometry, you can create those line bodies. Also, to control the properties being assigned to the line bodies, on the cross-section menu, we have a variety of options controlling the properties that will get transferred over to mechanical. So mechanical can use some standard, you can set up some standard cross-sections and input your dimensions, or with the user integrated, you can actually type in your area moment of inertia, your torsion constant, and so forth. In this example, I've created a user-defined cross-section, and when you insert a user-defined cross-section, I've identified this as my tube. You're actually switching into a 2D sketching mode, same sketching mode you use for planes, and you specify the cross-section. So I've created a cross-section of the similar profile of the tube, and this design model will calculate the properties for you. And then go ahead and assign those. When you select a line body, you can assign my tube as the cross-section type. So when you have the view menu turned on, display cross-section solids, that'll display this, and you can kind of confirm the geometry here. Another thing with the line bodies, let me turn off the visualization momentarily. One thing you want to create is, or want to confirm, is the orientation of the line body, because that'll define the orientation of your beam elements. With that, if you essentially switch over to edge select mode, if you select the line body itself, it actually switches the details pane for that line body and allows you to choose different methods of aligning the cross-section. So if you had an I-beam that wasn't aligned properly, in this case you can go ahead and select some geometry here to align it, or axis to align it. Let's say we wanted it this way. When we hit apply, this will define our Y-beam, our Y-axis of our line body, which defines the cross-section. So if I turn back on, you can see now that I've kind of misaligned our tube structure. So if this was the original way it was set up, we can go ahead, let me go ahead and select this and actually align this to the appropriate 3D edge here. Turn off the view, align it with this edge. Let's turn that arrow around. There's our Y-axis, aligning our cross-section. So now we can confirm back that we have our tube in place for the appropriate cross-section. Okay, so that's some setup with in Design Modeler. Let's move over to mechanical, see how our model is. I want to take a look at look at joining that line body of those beam elements with our surface body. Let's move over to mechanical here. Similar setup for our load. Our meshing here shows this as a line body meshed with beam elements. So let's take a look now. When we import our line bodies, a similar setup, you want to make sure you're assigning it the right material. You can offset the centroid of those beam elements if desired. With the line body, here's some visualization tools. When you highlight cross-section solids, that allows you, when you're selecting that line body, to visualize the cross-section, again, to confirm that it's coming into mechanical okay. Also, in this example problem, I've kept the bonded setup from our thin tube, our surface body tube, to the solid, and what I want to demonstrate is the ability to connect that line body to our surface. One of the ways I recommend doing that is the ability of using joints. Using joints, let me turn off our visualization there. Using joints gives you a method of connecting various types of geometry and controlling essentially the degrees of freedom that are being transferred across that. So from our joints menu, if we come over to our body-to-body method, I'm going to establish a fixed joint between the edge of that line body and all the edges of our surface body. You can see, let's set this up here. For our reference geometry, let me go ahead, select all the edges of our tube here, and this will be our reference. And then for the mobile section, I'm going to scope this to a vertex. That'll be the vertex of the end of the line body. Okay, with this fixed joint, you could see anything in gray is a degree of freedom that's being transferred across the joint. So we are taking all translation and all rotation degrees of freedom in this joint from the line body through to the beam. You have various options for limiting certain degrees of freedom depending on your analysis scenario. And that's helpful. Okay, so this will take care of the joint between the beam and our tube. So let's go ahead and take a look over at the results of that analysis. With this analysis, I want to show you some additional post-processing with beams and the connection with our joint here. Also, on the connections menu, if you are meshing primarily with beams, with line bodies and beams, you do have the option to include end releases should you want to kind of release some of the shears or moments on your beams. That gives you an option as well. Okay, looking at some of our results, you want to confirm, obviously, everything's working well. Looks like, based on our connection here, we have a similar deflection. Look at the load transfer here. You want to take a look at equivalent stress in our shells. Some additional post-processing for beams, you can look in terms of tools. You can look at a standard beam tool to do some of that post-processing. Some of the things I wanted to include for post-processing, let's take a look at additional post-processing for beams and shells. When you highlight the solution folder, you have the ability to take a look at the worksheet. Worksheet identifies all the results that are being saved to the RST file and made available to you through user-defined results. So you can see there's a lot of data being saved in the analysis. Well, down below, if we take a look at the type of results that's also there, you can see some beam-specific and shell-specific results. And so if you are interested in, let's say, a beam bending moment across a specific axis, you can highlight that, just create a user-defined results, and then go ahead and evaluate that results. And so you can, again, depending on the results you're interested in, go ahead and post-process those as well. So I've got a beam bending maximum sum. You can see that's the 100-pound shear load acting 15.5-inch moment arm to our end there. And then you can also look at various stress results from this is some bending stress in plane shear from some shell results if you're interested in that quantity. When I plot, sometimes when I post-process anything with MPC connections or the joint connections, I do like to, say we go to a force reaction, I do like to plot sometimes to visualize the connectivity. And you can do that by looking at selecting the solution information folder and display all your FE connectors, including making them visible on the results if you're interested in how that's being transferred across. One other thing I want to show in terms of post-processing this model is taking a look at the results across our joint. We set up our joint. Again, we set up our joint here. You can include a joint probe. Previously, we looked at the force probe in terms of evaluating the bonded contact. On the solution menu, you can evaluate joint probe as well. And this shows the 100-pound load of shear transferring across our joint. So from the solution menu, on the tools, from the probe, there's our joint probe. In this case, since I have the force joint probe there, let's go ahead and select this joint. Take a look at the total forces across there. You can also, let's go ahead and take a look at total moment on this one and evaluate that. And this will give you kind of a visualization of the moment coming across this joint. So there's our 1,550 pounds. So that allows you to kind of visualize the load transfer through the use of a joint probe. Okay, I think that's all I want to do for some post-processing confirmation here. Let's go ahead and take our next poll before I show you our last example. Our poll number 2 is just curious on what type of connection is being used by folks running analyses. You typically use bonded contact between your parts, or have you go ahead and taken advantage of some of the joint load transfer? Or do you really try to ensure you have matching meshes for that continuity and make sure they share nodes? And then for those of you familiar with mechanical APDL, do you specifically take a look at constraint equations or coupling between bodies, specifically perhaps within a mechanical APDL command script? So while we're taking that poll, I'll give you a few more seconds to take that. Let me close out some of my windows here and bring up our next topic. Okay, it looks like, taking a look at some of our results, looks like we have a mix. Some folks use bonded contact, some do use the joints, and then some have tried to ensure the matching mesh and the use of constraint equations. So it looks like a somewhat even mix. That's interesting. Okay, let's go ahead and take a look next at the next topic I want to cover is submodeling. And that, in the light of our topic of our webinar here, is working with shells, beams, and solids. We have the ability to do some submodeling when in considering shell models and doing submodels, detailed submodels. So let me bring up the other submodel here. While that's coming up, submodeling is a useful tool many folks employ to determine detailed stresses in parts. Quite often, building a larger model may be too coarse, important to get load transfer, but too coarse to produce satisfactory results in a specific area of region, such as a stress concentration factor or so forth. So many times you want to build a detailed, solid model of a localized region to get those detailed stresses you need. So in this example, we have a shell to solid submodel. So let me take a look at the global model. I used our beam model here, but I included an additional extra feature here. We've got a hole through our tube here. Perhaps we wanted to insert a pin as a pivot. We have a similar analysis in terms of load and boundary condition, but I've also included a joint. In this extra joint, I've included a cylindrical rotation about that hole. When we apply the same loads and boundary conditions, we can review the results. We have lower deflection, but now we have some difference in the change of the stress profile. So if we're interested in the details of this region, I'm going to go ahead and build a submodel of this region, include a much more refined mesh and all the features there. And that's what we have for our submodel. So let me switch over to our detailed local model. This is a completely, entirely solid mesh. So this is the only solid body here. We're making sure we've got the aluminum properties We also want to make sure when we set up our submodel that we include any interior boundary conditions in addition to the boundary conditions we're transferring through from the global model. So with this, I just want to show you the cylindrical joint we included on the solid model as part of the analysis, since this was interior in this local model, which was also included in the global model. So that is also included. Now, the whole challenge in running these submodels is transferring the boundary conditions from the global, especially when you have some perhaps arbitrary cross-sections or arbitrary locations. You want to take a slice and really transfer those boundary conditions. So what we have here, what I'd like to demonstrate, is the use of a submodeling ACT or ACT extension, Ansys Customization Toolkit extension. These are extensions where you can install. If I bring up our Workbench main menu, we have an extensions menu, version 14.5, that lets you install compiled extensions, whether we get them from the Ansys customer portal or we create our own. These Ansys, the extensions, let me bring up the customer portal. These are available from the download section in the extension library. And if we take a look at the ACT library, you can see some Ansys has made some of these extensions available. And so we're using the submodeling extension to support shell to or surface body to solid submodeling. Ansys Workbench in version 14.5, I believe, has already supported submodeling from solid to solid. So if you have solid to solid submodeling, all you have to do is drag the results from your global model over to your local model and set that up just by clicking and dragging and establishing the link. So it'd be from the solution cell, drag this over to the setup cell of your submodel, and then define the cut boundary interface. In this example, just to show you, it works very similar. When you have installed that extension, you see the submodeling. You essentially, with this submodeling menu, you can transfer the temperature conditions and the structural degrees of freedom. So I've inserted a structural degree of freedom in the outline tree, and this essentially defines how we're transferring the cut boundary location. So with this, let's walk through this in how we're transferring the boundary conditions. Essentially determine, let's select the surfaces of the solid as a method of cutting transferring the shell degrees of freedom over to our solid. So I've got that on both sides of my submodel. So those shells, translations, and rotations will get transferred across through translation degrees of freedom on my solid model. You merely specify the file name here. In this case, since I was building the global model in Workbench, I specified the RST file name throughout in the file structure. Take a look here. In the file structure of the Workbench project, we merely identify the correct RST file and then bring that and identify that in the details pane of the outline tray. What's also nice here is perhaps you may have built a global model or utilized a global model from a different Workbench project or a mechanical APDL database. Well, you can certainly link that RST file to this submodel which you built in Workbench. So it gives you a little bit of flexibility with legacy models or models, RST files generated from other sources. Next thing you want to identify in terms of the submodeling type, go 2D to 3D, 3D to 3D. In this case, this 3D geometry, we're specifying a shell to solid connection. And so this is what triggers transferring those shell rotations degree of freedom over to our solid finite element model. Once you have that set up, you can go ahead and post-process as you normally would in a submodeling procedure. We can certainly look at the local stresses and some of the things you want to do to confirm your transferring boundary conditions is take a look at the deformation. That the deformation pattern should be similar. So if I switch back to our original global model, I've identified in this this deformation here in this tube bend area. We've got a max deformation of 0.038. However, the pattern of the deformed shape or the pattern of the contour of the deforms looks very similar to our local model. We do have a little bit more deformation in the local model because it is transferring those rotations from the shelves to our solids. So we got a little bit more transformation. So you want to do those normal confirmation of making sure the boundary condition seems reasonable, transfer to your local model. Next thing you want to kind of review is the purpose of the submodeling method is taking a look at our stresses. If we take a look at our global model, that global model is showing some of the equivalent stress in this area as 16, a little over 16.5 KSI. And if we turn on our element edges, you see that's a fairly coarse model. One of the highlights of this local model is the mesh refinement. So if we take a look at the equivalent stresses with the element edges, you can see our peak stress prediction is a bit higher by 3 KSI in that region. And you can also show, perhaps some other hot spots or some other areas of concern. Our areas in the elbow area here look to be a bit bigger, and we can kind of confirm nothing too much going on in our holes. We are seeing a little peaking there. So that gives you an efficient tool to go from a submodeling procedure using shells to solids.